right, good morning, everybody. I didn't expect that much people, but we tried to entertain you guys. All right, let's go. First of all, I wanted to say that because of different NDAs on different projects, we can't show you like the real project we did. But this is like a full fictional use case we wanted to show you, but we collect all our experience and learnings into this fictional project. All right, how did we came up with the idea for the World Zoo Aurora? A few months ago, I went with my niece to the zoo, and she really wants to see every animal there. And yeah, we went there, and so I came up with this idea. And yeah, I mean, I'm not good in biology or my knowledge in animals. But as you know, little niece, she wants to know everything and want to see like, yeah, special animals. I don't know, but yeah. So I'm thinking about to make an AI chatbot named Wuffi for the search or discover different animals, because then we solve the problem that you're not an uncle or aunt that stand there and can't answer all the questions from your niece. And yeah, so here's Wuffi and how Wuffi works under the hood. Tim will help you then.
Yes, at least I will try. Thank you, Arne. If you were now tasked to build Wuffi yourselves, then you probably would have thought, oh, we need some kind of agentic system. And that's exactly what we thought as well. Let's get something with agents up. And so we went ahead and collected a couple of the components that I find very useful in vastly most of the agentic projects I do, especially if they have a knowledge base. So let's dive right into those components. First of all, of course, you need an LLM. Check, we did that. And then you need something that turns that LLM actually into an agent. In our case, we compiled a graph for that. We wrote our backend in Python, and we used LangChain and LangGraph in order to implement everything around the LLM and the agent. LangGraph, if you don't know that yet, Google that up later on. It's really tremendously helpful in order to build agents. We will show later on. We were using very small LLMs, so we tried to be very cost sensitive. Zoos, as you can imagine, they have a lot of costs already, and we didn't want to add to that list. So we wanted to be really sensitive with the costs. That's a pattern that you will see over and over again through this talk. So we've did a lot of measures in order to cut down costs. In our case, we've played around with Gemini 2.0 Flash and GPT-4 Mini, both fantastic models, and they worked to get this running. The intention was not to build an agent that is capable of like solving super complex tasks, but as Arne said, we wanted to help you guide through the zoo, find the animals that you're looking for. And for that task, they were perfect. And we did not host any LLMs ourselves. On the contrary, we let the hyperscalers do the work, and we worked with GCP and Azure on that. The second component was our knowledge base. You have that in basically every RAG project. In our case, there was an animal index where we stored all the 100,000 animals that our zoo had, like a tremendous zoo, imagine that. We used an open search DB for that was capable of semantic search. So we've compiled a lot of embeddings in there. Arne will give you a glimpse of that in more detail later on. But for now, just imagine huge database, a very smart semantic search can be applied on that. And we managed that through OpenSearch. Also, the zoo had a pre-existing software ecosystem and had APIs in there. Like imagine something like adding an animal to a route through the zoo or adding an animals to your favorite section in the profile. So there were pre-existing software components, and we were tasked with building an agent that would also be able to interact with those pre-existing APIs. Something that's very common across many projects as well when you think about your projects probably. And what we have done is we've created a lot of tools in order to make our LLM be able to interact with the world, be able to interact with our animal index and with the pre-existing APIs. Just to name a few of them, the most important ones, we created a search tool. That search tool takes a lot of input parameters and can then go to the animal index and do a very smart search and come up with around 30 potential animals that might be fitting to a request. Though this search is quite expensive to equip. not because the process of running the search in the database is expensive. It's more expensive than a keyword search, of course, but it's not expensive compared to LLMs, but because the tool is quite complicated to explain because of the many input parameters and the tokens that you need in order to explain how the tool works to the LLM. So remember that search tool is not cheap, and that will become important later on. We've then also created a select and show tool, and that select and show tool allows the LLM to pick the very best ones from the search response. So that gave us 30 candidates. The select and show tool can then select the very best ones, the most fitting ones to the user request. And we've wired this tool to the front end in order to actually show images of the animals. Because if you search for animals, of course, you don't want to get them back in text. You want to see pretty images. That's what the zoo tasked us with as well. Visitors were supposed to see images. And that's what that select and show tool is for. We've also created wrapper tools then, like an add to route tool or an add to favorites tool that were basically just wrappers around the pre-existing APIs so that our agent could interact with that. So nothing fancy on that. And if you were to take these components and just throw them at the vanilla architecture, just 20 lines of code if you don't have to write a functional backend with LangGraph, you would end up with an already working agent. And that's exactly what we started with. And I want to show you a quick demo of how that would work, just to get everybody on board. So we have a stage here, and we also have a little behind the scenes section. And what I want to do is I want to walk you through one customer interaction, one visitor interaction with our system, just to get everybody on board. So imagine we get a user request, find me a sweet animal. And then we would pull up our chatbot on the stage, and it would be tasked to answer this user request. And what it would do in the background is, of course, what chatbots are made for. It would talk. So it would say something like, of course I will search for you. And at the same time in the background, it would execute a search. It would use a tool in order to do a search. And that tool would go into our animal index, it would find potentially fitting animals, and it would feed them back into the context of the chat. And then with that enriched context, it would invoke the LLM once again. And in the second invocation, we would also, of course, that's what chatbots are made for, talk, and we would use the show tool if we've prompted everything correctly. And that show tool would then actually show images of the animals. And that would look a little bit like that. Here are some super sweet animals, and actually showing images of those animals. And with that, as usual, we've now called a tool. That tool would feed its response back into the context, and we would call the LLM a third time once again. And that would, again, do what agents are supposed to do and talk. And it would say something like, they are super sweet. And you can already see that there is kind of a redundancy in here. In our case, the show tool already does something in the real world. That's very uncommon for tools usually. Usually agents call tools, and then they get the response from the tools, and they are supposed to do something with that. In our case, the tool itself already does something. So we actually don't need the third invocation in here. This is almost always unnecessary, but it takes up roughly a third of the cost as we pay the tokens for each LLM interaction. So we wanted to get rid of that. And the second problem is that in the second invocation, most of the tools we provided were unnecessary. In real-life tests, we saw that almost all interactions with our agents were searching in the first invocation and then showing in the second invocation. But we provided all tools in each invocation. So in the second invocation, remember that expensive search tool, that was already in that each and every time, and we paid for that each and every time, although we never used it. And as the zoo was quite cost sensitive, we wanted to solve two of these problems, like these two. And we came up with possible solutions. And these are just ones of the solution. You could probably come up with others as well, but these we found quite helpful. What we did is we created another agent, one that's optimized for the second case, one that's optimized for selecting and showing. And we hardwired that to be called after the search tool each and every time. And we only gave that one tool, the show tool, and we forced it to use that. And that made this agent a lot cheaper than the other one. It has a lot less tools that we need to pay for, like the tokens, and we could optimize the system prompt to only be able to answer this showcase. And for the second problem, we implemented a finish check. And we hardwired this finish check to happen after the show chatbot did its thing. And that's a very cheap LLM call, which is tasked to assess whether we actually solved all customer tasks or did not. And if we did solve all customer tasks, then we just end the graph and the LLM interaction. And if we didn't, then we would invoke the LLM once again. And what I would like to show you is how this actually looks in the demo that we just did if you implement those two things. So imagine we have the same scenario. We have the stage. A user request pops up. Find me a sweet animal, same as before. We pull up our main agent. And then that main agent does the same thing as before. It just talks and it executes a search call. But now something changes. We pull up the show chatbot, since we hardwired that to happen after the search tool was called. And that show chatbot would now do the same thing as the main chatbot did before, and it would show some animals and give a text. But it would do that a lot cheaper. And from there, since we hardwired from the show chatbot to the finish check, we would now execute the finish check. And that would look a little bit like the following. Imagine the conversation that we've worked with now in the demos. Find me a sweet animal, and our agent said, okay, I will search for you, and here are some sweet animals. In that case, the finish check would say, bam, you're finished. And we could stop the interaction and wait for the next user request without doing that third unnecessary LLM call. But assuming that the user had said, find me sweet animals, and add the furriest one to my route. And we would have said, as the chatbot, of course I will search for you, and here are some sweet animals. In that case, the finish checker would say, we're not finished. And it would actually invoke the LLM once again, let the agent continue its way, and that agent would then probably use the add to route tool in order to add the furriest animal to the route. And I want to show you that in architecture as well, in case you're bored of the demo. This one is a graph architecture, and that's how LangGraph tries to depict agents and explain them. And what you see here is the most vanilla architecture that you can get in LangGraph. It starts at the start node, and from there we route to our agent. That's the general chatbot. And then a tool checker will check on whether a tool was used. If no tool was used, then we just end the graph. If a tool was used, then we route to that tool, execute that tool, and feed the results of that tool back into the chatbot again. And that can run as many loops as it wants until no tool is used anymore and we end. So the most vanilla architecture that you can get. And that's what drove the first demo that I showed you. And now come our changes. First of all, we loosened the connection between the tools and the general chatbot. And instead, we implemented a custom edge and checked which type of tool was used from the general chatbot. If the search tool was used, then we would actually hardwire to the show chatbot. If any other tool was used, then we would route back to the general chatbot. And remember, the show chatbot now only has one tool and is forced to use that. So from there, we wire to the show tool. And from the show tool, remember again, we hardwire to the finish checker. And that finish checker has two options for us. Either we are finished, then we route to the end, or we're not finished, then we route back to the general chatbot and let the circle begin again. And that's the agent architecture that we are now currently working with. We did a few minor tweaks in some points, but these are the main changes that we did that got our KPIs up by a lot, actually. Yes, so this is the architecture that we're using now. But what did we exactly gain from those two very simple things? I mean, in our production code, they are probably around 100 lines, I'd say, in order to implement that with LangGraph. And what we managed is to decrease our average cost by 35% just by saving tokens with that. We decreased our average latency of a conversation by roughly a quarter, and we managed to increase our reliability. Because remember, the zoo wanted visitors to see images of the animals. And before we forced it to use the show tool, after the search, the agent would sometimes just write text in order, oh, yeah, here there are some lions and some sort of animals. But now, since we forced it to use the show tool, users see pretty images of animals each and every one of the time they use it. And that's why we would recommend you to check your projects if there are any predefined workflows that you can leverage and that you can make use of. And we would encourage you to implement that into your agentic frameworks as well, because most provide the opportunity to have something mixed between agentic and predefined workflows. And in most of the cases, as we saw it, this combination of merging predefined workflows and agentic capabilities gives you the best balance between performance and cost. But for now, Arne will tell us a little bit more about how the search actually works.
All right, thank you, Tim. Yeah, let's dig a little bit deeper. Now Tim showed you like how the tools works, how the agents works, and yeah, let's see how the search is going on. All right. Yeah, we're mixing a lot of search methods to make like the best accuracy and to make the best yeah, picking up the candidates to make the best show tool. And how does it work? So we have the embedding search. I think that's the classic method everybody of you knows. So we encode documents, encode the queries, and put it into a vector space. Yeah, I think that's the classic thing, you know. Therefore, we need a good embedding model because in our case, we need an embedding model which works good with animals. So we have to look for that. That's also important, like to yeah, choose the right embedding model. This is also good for yeah, it's robust because of typos or different wording. But one thing we also learned is the multilingual embedding. It's because when all the character sheets from the animals coming from their original country, for example, there may be like description in yeah, specific words that just exist in their language, right? So that's why we need like a multi-embedding, multilingual embedding. So it works better in their own language. So we have like indices in their own languages. It's better than using multilingual LLM model. So we also have the multidimensional rec search, where we not only look into the vector space, but also looking into text or metadata, for example. Here, if you, so an example would be if you type in birds, so you're looking for birds in cold habitat, you're not looking also in the vector space, but also using like the tag with cold winter or the metadata with living environment, for example. We also combine keyword search for precise control and have like a hard filter, and it makes it more explainable. And also we boosting some important keywords, which is also important for the search for the right animal. Maybe you misses like cross-language things or synonyms, but that's fine for us because we want to push like just one keyword. Here, when you type in for search, for example, African elephants, so it's really look for African elephants and not Indians or like Asian type elephants. The last one is HYDE, like the hypothetical document embedding. So with the input from the user, we give it an LLM, and the LLM makes an hypothetical answer to that, which we retrieve then afterwards. So that's good if your query from the user is too short or too vague. For example, you just type in, I want a fish from Finding Nemo or Peppa Pig, and then it makes some examples of that, and then we're looking for the hypothetical query of that. Here, a little example. Find me a famous fish that kids know. And we gave that to the main chatbot, and then it provides like the first output, which we go to the search tool then afterwards. So we have like a summary with the most popular fish, for example, and the potential animal is the hypothetical query which the LLM makes. For example, here clownfish, seahorse, lionfish, and so on. Also have like an animal class and attributes like for kids' favorite. After that, it makes the search, and those are or could be the candidates for the show tool. Then we have, for example, a clownfish, seahorse, and so on. This is just an example how the candidates could look like. All right, now we know how the search working, but it's very important to have like a good database to make this whole thing works, right? And we also make a few specialty into our data pipeline. And yeah, that's what I want to show you now. data pipeline in index. First of all, you all know the medallion architecture, I think like with bronze, silver, gold, or here raw transform serving. And what we have added here are two things. The first thing is transform with LLM. The second thing is the index part. So I think most of the Gen AI or RAG use cases should extend those architecture with these parts. Why? Because first of all, we have a good database, maybe from the animal, but we still need more information to make the search works better. We have a few steps in here, like a translation, for example, or make a more characteristic list, meta tagging, and so on. I will go deeper later on. But also the part with the index, where we set up all the index properties, and also using an embedding model for the vector database afterwards. In this case, for example, we're using for the LLM part Gemini 2.5 Pro, and for the embedding part, we're using the text multilingual embedding from Google. How does it work? Or what does it mean? So here you can see like this is like the input or the database we had before, and after the pipeline running, we have more extension. For example, here it's a kids movie, true, small description, rarity, animal class. I just want to show you that we really extend all of our database and have like, yeah, a better database at the end. All right, how do we enrich here our data in the ETL pipeline? First I'll show you is the translation. This is important. Before, as I told you, that we build like different indices in different languages, and therefore we have to translate maybe some data for those indices. What is important here and what did we learn? Pay attention to dialects. So if you make a translation, you don't just have to prompt in like translate me into German, but thinking about like German Austria, or for example English UK or English Australia, for example. There are some different words or dialects that we have to think about and that we have to give to the prompt too. And one learning on the GPT model I've got is the infinite word repeat while translating. So if you're using the API too often to translate like bigger parts of texts, sometimes you just get like, yeah, it's so hallucinated that it's just repeat one word or different words to infinity. And yeah, you get a lot or often to the rate limit, and so you can see that. So, but in the Gemini model, it doesn't come anymore. And the translation works really well. So we tested it by LLM as a judge, and also tested it by real people who's looking into the data and gave us feedback. The second thing is image extraction. We not only pass an image, we just pass an URL and tell the LLM to open it and look at the photo in the database and yeah, make the extraction out of it. So we can extend our information, example here, nature, environment, and so on, but also give us a little summary of the photo, what the LLM sees there. So we can also extend not only by the description, but also by the photo. Next one is the characteristic list extension. So we extend it with synonyms, for example. So we have like a characteristic list from the animal, but then we extend it with synonyms, numbers of forms like singular and plural, and also have the information from the image to add on this list. Yeah, and we're also combining from different sources and languages for a bigger list. Therefore, we have like a really good list of characteristic for our search and embedding afterwards. and also meta tagging and text representation. Therefore, we're using tagging owned by the LLM, so we just prompted it and it makes it on its own for special features, for example, like habitat, danger level, but also the classification of animal. So classifications also works really well in our example. And we also do like a small one sentence description because you don't want to use like the big list, for example, sometimes because of saving tokens. All right. This is how all the things works and what are the learnings of those.
Yeah, and with that, we wanted to give you some nugget bits. That was quite a lot, probably. These learnings are a lot shorter. First one being LLM tracing is tremendously important. That's something that we saw. Whenever you work with agents, don't forget about LLM tracing. We've used LangSmith for that case. We've also set up an instance of LangFuse. And there are probably other solutions that we don't know about. But whenever you start agentic projects, think about LLM tracing as well. Otherwise, you will not understand what the hell your agent does. And we were in that case lots of times. Second one, at some point in our project, we defaulted to fine-tuning as our choice of that improving a lot of things. And we thought that this would be quite hard technically. And then we started with it, and we saw that there's literally a button in Azure and in GCP in order to start fine-tuning. And you just have to provide a data set, and it does everything for you. So technically, it's very easy. But then a couple of weeks later, we saw that maintaining the data set used for fine-tuning and having that in sync with the backend and the agent structure that you're currently developing, that is quite hard. So we spend a lot more time in order to actually manage our data set, and the technical part of fine-tuning was just clicking a button, at least when you're working with hyperscalers. That was a learning that we did not know before. Because previously we had fine-tuned local models, and that can be quite hard at sometimes. Then something else we would recommend is whenever you work with probably software, but especially AI software, do a phase into market. In that case, our customers wanted us to do a big bang. They wanted us to release everything to the world in one finished state. And we tried very hard to disengage them from that idea. Because when you work with AI and your product hits customers the first time, you will get feedback which you did not think about before. That's true for software, but especially true for AI. So what we convinced them to do is a launch with a phase-in, like where we extend the user group every couple of weeks. And that worked a lot better than if we just had opened our product to the whole customer base before. So really have that in mind and try to convince your stakeholders that that is a good idea. Because they might sometimes not understand how random AI can be. Because they think it will just work out of the box. And then something that we've seen, especially when your customer is cost sensitive. The best thing that you can do in order to cut down costs on LLM projects is to not use LLMs. That's really the single best thing you can do. And for that, traditional caching can be often overlooked. So whenever possible, try to implement methods of traditional caching, cache embeddings, for example. If applicable, cache whole agent responses. In our case, when the same user, like when another user asks for the same search pattern again, we will just stream a cached response and make it seem like the agent is generating that, although we've cached that. And then you can also, with LLMs, use context caching for things like your system prompt or your tool descriptions. Most hyperscalers provide that basically out of the box, where you can pay a lower price for tokens for things that you reuse often. Imagine system prompts. And then I think on Google, it's currently a quarter of the price that you pay for that cached component. And that can really add up, especially if you have long system prompts or long tool descriptions. But then again, mistrust, double check, and verify documentation in all AI fields. For example, in our case, it was just the case that the context caching was not working with the specified version of our model in combination with the fine-tuned model. And it was not listed anywhere on the documentation. So we communicated with our stakeholders and said that to them that we will get reduced prices, when in reality we wouldn't, which we only saw when we developed it. And then we saw that in a couple of other instances, documentation is lacking behind in the field where we develop so fast. Like AI is moving so fast that documentation can sometimes be apart from reality. And what we've seen especially is that German documentation is lagging behind even further than English documentation because English documentation is the first one that's being actualized and renewed, and then it's getting translated in most cases. So if you can, always read English documentation and mistrust that still. And then again, regarding costs, most cloud providers provide you the option to reserve PTUs, so that you have reserved capacity, computing capacity, and then you can trust that capacity to be there always for you. But they charge you a premium for that. That's different than traditional computing, where you say, okay, if I take X amount and I pay for that upfront, I get cheaper prices. With LLMs, it's actually the opposite, so you have to pay a premium. And then there is pay-as-you-go, where you pay per request that you do. But that might be rate limited at some point. And it's really about getting a combination of those two to work and having smart load balancing in order to still have your platform or your system be reliable and answer each and every time, but make use of everything that you can in pay-as-you-go in order to cut down on costs. So we wouldn't recommend having just 100% PTUs because you will pay a shit ton of money then. And with that, let's move on to some other learnings from the index.
Yeah, there's some few points I want to add. The first one is to async your LLM payload, because in the ETL pipeline we can see that yeah, we need to do that to get the whole use of the API, and also get to the limit of it, and also to get a better utilize of your cluster. And also load balancing and batch processing. There's often that you can't or you don't have an automatic load balancing from Google, for example, but we build our own load balancer to switching the regions, so you get less of the 429 error of rate limit, and it works perfectly. And also batch processing, there's the hint. Also look into the documentary. Not all APIs have batch processing. For embedding sometimes, but not for the LLM calls. So this is also important where you can save some money. And the last part is here are a few keywords we wanted to show you. Maybe those can be important for you. Those were important for us. And most important thing I would say is for us the Pydantic model. There's a library in Python where you can bind your LLM results into a structured output. This helps us a lot, for example, in the ETL pipeline, because we need, for example, we give in some list sort of structure, but we need it in JSON format, and so you can bind your result into a structure with Pydantic. All right, this was our learnings. Thank you very much for joining. We have a few minutes time for question, I guess, but you can also scan the QR codes and connecting with us. We're here the next few days, and I'm sure we don't have the best solution for all of those, but yeah, we are open for discussion. So if you have any ideas, just come to us.
Definitely, thank you.